The rational root theorem is a way to help us find some zeros of a polynomial function, especially when those zeros aren't very obvious from either the equation or the graph. The rational root theorem, also known as the rational zero theorem, reads as follows. If a polynomial has integer coefficients, the only possible rational zeros are in the form factors of the constant divided by factors of the leading coefficient. Some or even all of these numbers may not turn out to be zeros, but we know that no other rational numbers can be zeros of this polynomial. Any other zeros must be irrational or imaginary numbers. So let's look at an example. Find all of the possible rational roots or zeros of the polynomial f of x equals 2x to the third plus x squared minus 13x minus 5. Now, taking a look at the graph of this polynomial, we can see that there aren't any obvious integer zeros. So how do we go about getting started? It's not a factorable polynomial. You can see the 2x cubed plus x squared minus 13x minus 5 can't be factored by grouping, so there's no real obvious way to find the first zero. So going back to our example here and the rational root theorem, we take the factors of the constant, which is negative 5, and the possible factors of negative 5 are either positive and negative 1 or positive negative 5, divided by factors of the leading coefficient, which are positive and negative 1 and positive and negative 2. Now, if you're wondering why we do factors of the constant divided by factors of the leading coefficient, think about it this way. If we have a degree 3 polynomial, we could first factor out the leading coefficient, and then we would have three factors of x plus or minus something. And we know that 2 times this constant times this constant times this constant has to equal negative 5. So it makes sense that these numbers have to either be factors of 5 or they have to be factors of 5 divided by 2. Actually, that makes more sense, that these three numbers have to multiply to give me 5 halves, or negative 5 halves, because negative 5 halves times 2 would give me negative 5. So it makes sense that the rational numbers that could go here would be numbers like 5 halves or 1 half, positive or negative. Now, not all of these numbers are rational numbers necessarily, and not all of them necessarily have to be rational numbers at all. But if they are rational numbers, they have to be one of these numbers, 1, 5, 1 half, or 5 halves, either positive or negative. Get back to where I was before. So we have 8 possible rational zeros, positive and negative 1, positive and negative 5, positive and negative 1 half, or positive negative 5 halves. And just to re-emphasize, remember that this doesn't guarantee that any of these 8 numbers is a zero of f of x, just that no other rational number can be a zero of this polynomial. If we look at the graph, we can see that negative 1, positive 1, negative 5, and positive 5 are definitely not zeros. But we do see this right here, which looks like 5 halves, 2 1/2. This is possibly negative 1 half, but it doesn't look like it's quite in the middle. And it turns out if we were to trace the graph, and we typed in 5 halves, 5 halves does turn out to be a zero of this function. Now, how is that helpful? Well, if we know that 5 halves is a zero of the function, then we know one of the zeros. This is a cubic. We can use the 5 halves then in synthetic division to divide down the cubic into a quadratic, and once we have a quadratic, we can use the quadratic formula to find the other two zeros. So this eliminates just trial and error trying to figure out that first zero. Using this list of 8 numbers and the graph, it was clear that 5 halves was the best choice. Trying that, we would find that that is a zero. Just a reminder, rational numbers are numbers that can be written as the ratio of two integers, such as -2/3 or 4, which can be written as 4/1. In decimal forms, they are terminating or repeating decimals like 1.25 or 0.666. Irrational numbers are non-repeating, non-terminating decimals. Examples are non-perfect roots, such as the square root of 5 or the cube root of 4, or numbers like e or pi. The irrational numbers we will find as zeros will involve square roots. It is not always necessary to use the rational root theorem when finding the zeros of a polynomial. Sometimes you can find the zeros quite obviously from the graph, or by factoring, or by using synthetic combination of the synthetic division and factoring. But if you are stuck and you need to get started finding the first zero or the first two zeros, often the rational root theorem can be helpful in limiting the number of possibilities to try.